There are at least 100 to 400 billion stars in our galaxy. Imagine if each star had just one planet. That means there could be up to 400 billion planets in the Milky Way alone. Now think about this. The universe has around 2 trillion galaxies, which means the number of stars out there is incredibly huge. Some estimates even suggest that there are more stars in the universe than grains of sand on all of Earth's beaches. That could mean just as many planets. But here's the strange part. Despite all these possibilities, we haven't received any signals from extraterrestrial life. There's no solid evidence that they're out there trying to communicate with us. This weird situation, where the odds of finding alien life seem high, but we have no proof, is called the Fermi paradox. It asks the simple but profound question, where is everyone? Now, scientists might have uncovered a clue to solving this mystery. They've discovered that our galaxy is positioned near the center of a massive cosmic void known as the KBC void, or the local hole. This void, which stretches an incredible 2 billion light-years across, challenges some of the most basic ideas in cosmology. The existence of such a vast, empty space raises big questions about the Big Bang, how galaxies are spread out, and the very nature of the universe's expansion. However, the most intriguing part is that this void could help explain two of astronomy's biggest puzzles, the Hubble tension and the Fermi paradox. So, how did astronomers figure out that we live in a mysterious cosmic void? How does the KBC void challenge our standard model of cosmology? Finally, and most importantly, how could it explain why we haven't received a message from another civilization yet? Astronomers discovered the KBC void by examining the distribution of galaxies in the nearby universe. This groundbreaking discovery was made by Ryan Keenan, Amy Barger, and Lennox Cowie. The researchers used galaxy redshift surveys, which measure how the light from galaxies is shifted due to the universe's expansion. This method allowed them to create a three-dimensional map of galaxy distribution, revealing regions with fewer galaxies. Their analysis uncovered a spherical region approximately 2 billion light-years across, characterized by a notable lack of galaxies compared to surrounding areas. This void is about 7 times larger than a typical cosmic void. At first, researchers met the idea of the existence of such a void with doubt because it poses significant challenges to the standard model of cosmology. There are 2 main problems. The first is the cosmological principle. The significant lack of galaxies in the local hole challenges the idea that matter is evenly spread across the universe, a key assumption in our current understanding of cosmology. The second problem is simulations. Cosmological simulations, like the MXXL simulation, suggest that forming a void as large as the KBC void is unlikely under our currently accepted Lambda-CM model of the universe. According to these simulations, the gravitational forces predicted by this model aren't strong enough to create such a vast and deep underdensity. However, as more observations and data were collected, the existence of this massive void became undeniable. Surveys and telescopes consistently revealed a significant lack of galaxies in this 2 billion light-year wide region. But astronomers soon realized that this void, despite initially posing a problem for our models, might actually hold the key to solving one of the biggest challenges in cosmology, the Hubble tension, a problem that has puzzled scientists for over 6 decades. Just like figuring out a vast cosmic void, navigating the web can sometimes feel overwhelming. So much information and tabs. That's where Opera's AI, Aria, steps in. Instead of surfing through countless web pages, Aria, conveniently located in the sidebar, provides clear and instant answers. It connects you to real-time information and generates content based on your ideas with just a few clicks. You can explore and translate any highlighted text on a page with Aria. And when you need a bit more organization, Tab Island comes to the rescue. You can effortlessly group your tabs by context, news websites, workspace, social media, and save space by collapsing islands. This feature makes sure you stay focused on what matters most. Plus, the built-in VPN offers private browsing, hiding your location and keeping your activity secure without logging any information. Another feature I adore is Opera's Battery Saver. It lets me browse for up to an hour longer without needing any extensions and takes just a single click to activate. This built-in feature ensures I can keep exploring the wonders of the universe even when I'm away from a power source. So, click the link in the description to download Opera for free and transform your internet browsing into a seamless experience. Now back to the cosmos. The fact that we live near the center of a giant cosmic void can resolve the biggest cosmology crisis, the Hubble tension. Hubble tension refers to a puzzling disagreement about how fast the universe is expanding. To understand this, let's break it down into simple parts. The universe has been expanding since the Big Bang, and the rate of this expansion is described by a number called the Hubble constant. Think of it as a speed limit for how fast galaxies are moving away from each other as the universe gets bigger. There are two ways to measure this expansion. The first is the direct method, which involves looking at the nearby galaxies. Astronomers use special types of variable stars and supernovas to calculate distances in space. Then, they measure how fast these galaxies are moving away from us. This gives one value for the Hubble constant. The second is the indirect method, which involves looking at the cosmic microwave background, the afterglow of the Big Bang. This light has been traveling for over 13.6 billion years and gives us a snapshot of the early universe. Using a detailed model of how the universe has evolved since then, scientists can estimate what the Hubble constant should be today. Here's where the tension comes in. The Hubble constant calculated from nearby galaxies and the one estimated from the early universe don't match. The value from nearby galaxies is about 73 kilometers per second per megaparsec, while the value from the early universe is about 67 kilometers per second per megaparsec. The discrepancy between these two values may seem small, but it is statistically significant and beyond the expected margins of error for such precise measurements. Also, it introduces uncertainties in our estimate of the age of the universe. The universe's age is often estimated by running the clock backward on the expansion. If you know how fast the universe is expanding now, or the Hubble constant, you can estimate how long it has been expanding to reach its current size. This gives you an estimate of the time elapsed since the Big Bang, which is the age of the universe. A higher Hubble constant suggests that the universe is younger, around 12.5 billion years old, while a lower Hubble constant indicates an age closer to 13.8 billion years. This difference in the Hubble constant results in a staggering 10% age discrepancy. The Hubble tension is a big deal because it suggests that something might be missing or misunderstood in our current understanding of the universe. It could mean that there's new physics to discover, something beyond what we know about dark energy, dark matter, or even the nature of gravity. However, another simple explanation to the Hubble tension is our unusual place in the universe. Inside the KBC void, there are fewer galaxies and less matter compared to regions outside the void. This lower density means that objects within the void exert less gravitational pull, while the surrounding, denser regions exert a stronger gravitational force, pulling objects toward them. This creates the illusion that the local universe is expanding faster than it actually is because we are being pulled by the gravity of objects outside the void. When scientists analyze the matter density inside the KBC void up to a distance of 300 megaparsecs, they found it to be about 20% less than the universe's average density on larger scales. This lower density within the void correlates with previous studies showing that the expansion rate measured locally is about 11% greater than the true expansion rate. Essentially, the gravitational effects of the denser regions outside the void give us the impression of a faster expansion, which could explain the Hubble tension. The existence of the KBC void also challenges the lambda cold dark matter model, which is the most widely accepted and successful model of the universe. Based on early universe density fluctuations and the uniform distribution of matter on large scales, this model does not predict the formation of such vast empty regions. However, when scientists adjusted the initial density fluctuations and increased the efficiency of structure formation in their simulations, they found that voids like KBC could form. But there was a catch. Their simulations no longer matched the LCDM model. Instead, they used an alternative theory called modified Newtonian dynamics, or MOND. originally proposed to explain the strange behavior of galaxy rotation curves without invoking dark matter. Mond suggests modifying Newton's law of gravity rather than adding invisible matter. The two main differences between LCDM and Mond are as follows. First, Mond replaces the need for dark matter by altering how gravity works at low accelerations. Second, Mond predicts that galaxy and galaxy cluster growth happens faster than in the LCDM model. This accelerated structure formation makes the existence of voids more likely in a Mond universe. The tension between these two theories remains unresolved because some cosmic observations support Mond, while others align with the LCDM model. As a result, there is no clear winner in the debate between these two competing ideas, leaving us with an ongoing mystery about the true nature of the universe. The KBC Voids discovery indicates that some cosmological principles may need to be revised or abandoned in light of new evidence. If the universe exhibits significant local variations in density, it could necessitate a re-evaluation of fundamental cosmological